Sir, sir, sir. Hello.
Yes, ma'am. Hello.
Okay, now the audio is audible, sir.
Okay, okay. Till now it was not audible.
Just I came 1 minute to
Okay,
ago.
okay. No worries. Actually, I think so. The cord got loose. So, this I'm just explaining the important concepts.
Okay,
Uh,
sir.
we'll just move. So this is a very important thing. It may be like it might not be in the part of the lecture, but it is coursework. But it is an important thing that this is a Moore's law. If you are studying MEMS, and if you are putting this in your in thing, so you need to know Moore's law. So basically, it says that the number of transistors doubles every 2 years. So you can see from 1971, the transistors in 4004 microprocessor were 2250. In 2004, Pentium 4 microprocessor, the number of transistors you can see it's 10,000 lakh, 10 lakh, crore, 12 crore, 50 lakh transistors. So the number of transistors has been doubling every year, and now it is being said that because the development is so fast in the field of micro photolithography, Moore's law might get like till now the Moore's law has been obeyed. It might not get obeyed in the near future. That is what with the advent of AI and all those things. So this is an important law. So how a basic MEMS process actually works. So you have a silicon substrate, that is a pure silicon substrate. Then you grow oxide layer on it. Then once you get the oxide layer, then you deposit the resistor material. Then you pattern the material. So basically you do like photolithography and etching. Then again you deposit the insulator material, like you deposit using PVD or CVD. Then you can again pattern the insulator material. Then you can again deposit metal and pattern metal, so that you can it goes on, the entire process goes on. So that is how the entire our typical MEMS fabrication process looks like. So now, as I showed you, you need a pure silicon wafer to get the uh, uh, to actually make the MEMS process. So actually, if you get if you use a normal silicon, anything normal silicon wafer, it will get what will happen is it will have a lot of grain boundaries, so that will not give proper results. So you need a single grain. So that is why what they do is basically you use a special process for making the silicon wafer also. So that is called as the Slozarki process. So basically, what you do is you melt the silicon, then you use a seed and you just pull it out. So you pull it very slowly, so that you can get a entire rod. This rod is basically this rod is a silicon rod, and then this rod is basically cut into wafers using diamond sauce. So that is how it actually works, and this is a very important process that is used. So now coming to what
Sir, is the process is manual or automatic, sir? Uh,
automated. So everything in MEMS, you will get most of the things will be automated. So even
okay.
in the clean room, what I can show you in this clean room. So there'll be this is how a clean room looks like. So what will happen is you'll have this full clean room. One will be photolithography. So you will enter from here. You will first take the wafer. So you will enter from here, but wafer will come from somewhere else. So there will be a material loading area. So this is not a very exhaustive design, but there will be material loading area. So you will take the wafer. So once you enter, you will take the wafer. You will first sterilize it using ethanol. You will clean it. Then you will use all the photoresist. So photoresist will be like the positive photoresist or negative photoresist, whatever is there. It will be there'll be a recipe for everything. So in the clean rooms, there is everything is automated. So you will just take your wafer, you will clean it using ethanol. You will place it in a spin coater, and you will put your resin. Even the RPM at which the thing has to rotate is fixed. So everything is fixed and everything is automated. Then you take the wafer. So only loading of wafers and those things actually require some input from your end. Otherwise, it's just uh, otherwise everything is automated only. Where your talent is basically is changing the parameters. So where the engineer actually plays a role is changing the parameters. So if you are having a PVD, if you like what you have to do. So the design part is the only where place where the actual talent is. So the processes are fully automated. So process you nobody needs to actually do anything. So it's the design and the understanding of the systems. So that is how what you are expected from a MEMS engineer.
SSA. Okay, sir.
So this is one of the important formulas you need to know to find the angle between all the crystallographic directions. You need to know the formula for finding the direction, the angle between the crystallographic planes. So you have two crystallographic direction, U1 V1 UV W1 and U2 V2 W2. So you have to find the angle between the two. You are using this formula. Then again, now everything is done. We made the wafer and everything. Obviously we are using a silicon. We have to dope the silicon wafer. So we need to find out what kind of doping has been done, whether it's a N-type semiconductor or a P-type semiconductor, and what is the etching, what is the plane, what is the crystallographic direction of the silicon that is there in the wafer. So even to do that, there is a very good standardized practice. So this is how P-type semiconductor looks, this is how a N-type semiconductor looks. So P-type is P-type 111 is basically flat at the bottom. N-type 111 is flat at the bottom but also has a cut at 45 degrees. uh, P type 100 again. Basically, it looks like it looks the same, but N type 100 basically it has flat cuts at both top and the bottom. So that is how it looks, and that is how you can
So,
identify.
is there any condition to have 45 degrees angle in the 311 N type vapor, sir?
No, no,
For
this is how
45.
you have to identify. So now what will happen is when you are going into the so so all these things don't happen at the same place. So there'll be one place where the wafer is being made. So the wafer will be brought from some place, and it will be given. So now you have to identify, no, if they don't maintain a standard practice, if the standards are not maintained. So now basically when you are making any wiring, so the red one is supposed to be the live, black one is supposed to be the neutral, and other one is supposed to be the ground. So how we the wires are color coded so that any electrician even later can identify and he can fix your house wiring. So that
Okay,
same
sir.
way, so somebody has to identify from the wafer type what the type of wafer is. So for doing that, these this is how they cut it. So when you're whenever a manufacturer is manufacturing a N type 111 silicon wafer, he will have to cut it this way so that the person can identify. So this is the identification pattern you need to know, so that how will you, if they'll ask, if they are some, like they might not ask in exam these questions, but I'm giving you a hint. So if somebody has is putting this course in their CV, and so these are the questions they may ask then during that time, because there is a lot of demand going on for MEMS engineer in India, because now obviously there is a semiconductor mission also. So these are the, they will not ask in when they'll because every nobody knows anything. They'll ask very basic question during the interviews, and these are the questions which might help them, help the student. So i I've just made the generalized slide so that it can help whoever wants to put this in this course as in their CV, and go for the opportunity in the silicon industry, silicon
Sir, what is 110, sir? In the middle, triple one is there. In at the bottom, 110 is there.
so triple one is the direction, and So uh, so in crystallography, there is one as crystallography plane, and then there is the vector of the plane. So vector is basically perpendicular to that plane. So I'll just show you in the previous slide. So you can see this triangle here. So this is called as a crystallographic plane, and then there will be one crystallographic vector. So basically that will be pointing. So you can see here. If you can see, I'll just draw and show this is the plane, right? This one is the plane, but if you can see
That is a
here,
triple one, sir. That is a triple one plane.
plane, and so you can see the
Okay.
vector here, you can see the line going on here. So this is called as the vector. So this vector gives the like this is actually perpendicular to the plane. So this gives you information about the plane basically. So if you take a inverse of the direction, you get the plane. So that is how it works basically. So
Sir, then 110 is perpendicular to triple one and to the 100, sir. To both.
uh, yeah, uh, I think so. There is some mistake with this 110. You just this I'll just get back to you next time.
Okay,
This
sir.
this is something I think so there's some
At the
mistake. I'll
center, it is okay, sir. It is matching. Center in the previous class, these are true, sir. In the middle, whatever syntax is there, that is true, sir.
This thing I think so there is some problem. I'll just check. I'll just check. Maybe uh, there might be some mistake in this figure. I'll just check and I'll get back. So we'll move to the next thing. This is called as the oxidation. So as I said in the previous in the entire workflow, you need to once uh, you get the wafer, you need to grow an oxide layer on it. So basically, to grow the oxide layer, there are three types of oxidation processes. There is one is dry oxidation, the second is wet oxidation, and the third is pyrogenic or the steam based oxidation. So basically, what you do in the first dry oxidation is you use nitrogen and oxygen, and you grow a oxide layer. In the wet oxidation you have water kind of thing, so you put water also. So basically wet oxidation is faster than dry oxidation, but obviously the control or the control over the oxidation layer is obviously better in the dry oxidation process. Pyrogenic is in the middle of both processes. It is a more efficient process. It uses steam, and you get the oxide layer. So dry oxidation best control over the uh, thickness, oxidized film thickness, very slow. Wet oxidation, poor control but very fast. Pyrogenic is in middle. It gives good control as well as it gives better faster results also. So then after this the oxide layer, the next step was basically you have to do the photolithography. So basically in photolithography you take the wafer and you put that on the chuck, and basically you dispense the resin on the wafer. So here you have the rotating chuck on which the wafer has been put, and from the dispenser you are dispensing the photoresist. So photoresist can be a positive photoresist or negative photoresist, uh, but in either case you have to dispense it. So basically what you do is you dispense just at the center of a small amount. With the speed of rotation the entire liquid will get spread. So here you can see the different ways the liquid can get spread. So you have to optimize the speed. So as I said earlier, the recipe will be given, so the speeds and everything are optimized for that resin for that condition, so that you get the best result. So what happens in this one, the it will the thick the film is too thick and it is uneven. So in the first case it is too thick, in the second case it is uneven. So in both cases what will happen is you have to since after this process you have to do lithography. So you will be passing and you will be passing light through it, and you will be solidifying some areas um, of this resist where you have put the resist. So it is very important that you get the thickness right. So to get the right thickness, you need to get the right rotating speed and everything. So those parameters have already been have to be done using. So the you can, from this chart you can maybe get an idea of how the variation happens. So using various parameters such as the rotating speed of the chuck, the viscosity of the resin, and various other things factors, they develop the optimal recipe for that clean room. So whenever you go into a clean room, you will get the optimal recipe for that specific photoresist. So after the photoresist has been done, the next step will be basically exposing it to the mask. So basically there will be a mask will be put on the wafer, and you will be exposing it. So basically you like be exposing it to light, and then the specific areas will harden. So basically depending on which type of photoresist you are using, in case of negative photoresist, the area which has been exposed will not get hardened. In case of positive photoresist, the area which has been exposed to light will get hardened. And after that, basically, what you will do is you will wash that off. So this has been this area, you from the previous process, this area has been hardened, and you got this area hardened. So now you will etch it. So basically you'll drop an etchant, and through an etchant you will remove the area below the mask. So then there are two types of etching. There is one is isotropic etching and one is anisotropic etching. Isotropic etching is basically etching in all directions. So basically here, once you drop the etchant will spread in all directions, as you can see here. Whereas anisotropic etching is is the axis specific etching. So basically what will happen is, it's not that like what it is shown in the figure. So it will not be like etching will happen only in along one axis, but what will happen is etching, if etching rate along the z axis is like 10 millimeter per second, for along x and y axis it will be like 1 millimeter per second. So that will be that, in that way you will be able to get better etch rates, and you will be able to get better results in that sense. So to know how the etching will work and how much what will be the etch rate and everything, so you have to use this triangle. So this is the triangle. So here you have nitric acid, hydrofluoric acid, and uh, acetic acid. Yeah. So so using this etching triangle by for every composition. So if you have 100% of hydrofluoric acid, you will get this much etching rate. So 90% of uh, hydrofluoric acid, uh, the HNO3 70% will always be 70%, and citric acid again, acetic acid, sorry, will have specific rates, and based on this line you will get to know your etching rate
Sir,
for that
what is the
etching.
third parameter, sir? On the curve, what is the third parameter?
These are the
That is
etching rates. These are the etching
etching
rates.
rates. Okay.
This is the concentration, and the weight percent. So basically, this is the concentration. The concentration will be 49% HF, 70% HNO3, but the weight percent. So like 70% HNO3, basically you mix 70% nitric acid in, and 30 ml 30% water. So you will make that solution. You'll have hydrofluoric acid solution, that will be 49% hydrofluoric acid, 51% water, and you'll have the acetic acid solution, and then like
Sir,
weight
we are
percent.
mixing all the three, sir, now?
Yeah, so depending on this, so
Only.
like here what is happening is, here you have 0%, sorry, yeah, here you have 0%. So in that solution what you are having is, here you have 0% of hydrofluoric acid and 100% of acetic acid. So that here, this will be the etching rate. So in this case, so what is happening is, you have 60% of hydrofluoric acid, 60% of nitric acid, and 40% of like uh, like actually basically it's 60% of hydrofluoric acid and 40% of acetic acid. The concentration of nitric acid is more or less the same. So based on that you will get this H rate. So you will get an H rate of 7.5. So if you
Sir,
increase it, if
sir, you have told here 0 and 100. And no curve is there. That means here etching is not
Etching will not happen. Etching will not happen, or basically that is not worth pursuing. So
okay, sir.
you have to have that optimal area, no? So now here what we will have do is, if you have 100%, if you have 90% of hydrofluoric acid and 20% of acetic, 10% of acetic acid, you will get like this kind of curve. So it is something, basically you need to find understand it more. Maybe you can go through a YouTube video to understand this. But what the main core understanding from this course is basically this kind of curve exists. So to go in deep, you need to maybe go on YouTube and search it. But for this course, we only need to know what is the, like, what is this curve called. Uh, so then there's one more agent. So basically, this is a very important agent that has been maybe shown in the course as well. So tetramethyl ammonium hydroxide. So this is basically a organic, as you can see here, it is a tetramethyl ammonium hydroxide. It is non like, you don't have any corrosive acids, like you don't have any nitric acid or hydrofluoric acid. This is a low toxic agent. So it is low, it is low toxic, and it is highly selective. So as I said earlier, we need an anisotropic or a very highly selective agent. So that is why this is a very highly selective agent. It has also a good, it is highly selective to oxide and nitride compared to KOH, and it also has good H rate, and it is highly compatible with the CMOS processing. So this is a very important agent. So this is not the part of the previous chart we studied, but this is also part of your syllabus. So basically, you need to know about this agent also.
Sir, what is the meaning of highly compatible with CMOS processing?
So basically, for highly compatible is basically you need an isotropic agent. So compatibility with CMOS is basically dependent on whether it is giving anisotropy or not. So if it is an isotropic agent, you will not get any directional accuracy, right? It will get H. Everything will get H. No, since everything will get etched, you will not get the directional control. So to get directional control, with the agents which give good directional control are the most preferred ones with for etchings. That is why this is compatible. And the other thing is, it should be washable. So what is happening is, the etchant should get washed out after its work is done. Like we should be able to stop the etching also, because if it just eats up the entire wafer, the wafer will be in the micrometer scale. So it will be 2 micrometer or 3 micrometer. Even now, even the nanometer silicon wafers have come into place. So you have to be able to wash or stop the process also. So that makes the, like, how good it is, in that sense, makes the agent desirable or non-desirable. That is the main crux of that thing. So moving to the next thing. So after, as I said, as I showed here, so you have done the etching. So we'll just move back to this slide. So we got the wafer, how the wafer is made. We understood that. We understood the grow oxide uh, part, that wet etching, dry etching, and pyrogenic that process. So then we also understood how the deposition is happening by spin coating. As I showed, the chuck will be kept, the wafer will be kept on the vacuum chuck, and you will deposit the resin. So then pattern resistor material, as I told you, it will be photolithography process. So you'll have a mask, and then there will be hardening and washing out. So now we come to the next part, so which is the deposition of the insulator material. So depositing the material. So here the deposition time kind of process we are coming to. So there are like two main important deposition processes. One is PVD and CVD. Here, this is a schematic of PVD, physical vapor deposition. So this will be an argon atmosphere. So you will have argon, fully argon gas. You will have the substrate. So basically, here you will have the silicon wafer. So what will happen is, argon will get ionized. It will go and hit. So this is a gold. This is gold basically. So what will happen is argon will get ionized and it will go and hit the gold. The gold will eject gold atoms. So gold atoms will go and hit the silicon that's substrate. Basically, because it will be, there will be a potential difference. The sputtering target, basically it will have, so one will be connected to the positive terminal, one will be connected to the negative terminal, and the ejected ions will go and hit the substrate and basically get deposited. So you'll get a gold layer on your on your substrate. So this is how the entire PVD process works. In the CVD process, basically chemicals are used for deposition. So the atmosphere and those things change. It has CVD. I don't know whether they have given in this course or not, but it is somewhat more simple compared to PVD. But PVD gives good control. Obviously, it will give good control over the dimensions, but it will be a slow process in the chemical vapor deposition. The chemicals in the vapor form will go and directly get deposited on the wafer. It is a faster process, but again you will not get a very control over the film thickness. So that is the processes. So we'll move. So as I said, based on this slide, I have explained most of the things. So substrate, how we make the substrate, how we grow the oxide layer, how we deposit the photoresist, how we do the photolithography, then how we do the etching and everything, and how we deposit the metal. And then again, for patterning the metal, again you will have to do the same thing. You will have to deposit the resin and do the etching part. So basically the processes will, you'll keep on repeating the process in a cyclic manner to get what you want. But the major processes are these things. So oxidation, photolithography, etching, and deposition. So basically whether a physical vapor deposition or chemical vapor deposition. These are the major important processes. You will it is basically the talent of the designer or talent of the MEMS engineer to make the cycles, how you do the final design of the circuit. So we are done with the major concept. So we'll just move to the first question. What So you have this question. So you have two planes. So how will you find the angle between them? So you have the plane 121 and 110. So the options are 54.7, B 75, C is 50, C is 30, and D is 45. So I just showed the formula in one of our slides. So this is the formula basically. U is so you will just substitute U1, V1 and W1, and U2 V2 W2, and you'll substitute in this you know in this formula, and then you will get the angle between the planes. So the angle is basically inverse of cos 3 by 2, which is 30 degrees. Any questions?
Okay, sir.
So we'll move to the next question. Which of the following is an isotropic agent? 30% KOH solution, HNA agent, EDP at 1150 degrees Celsius, TMAH at 700 degrees Celsius to 900 degrees Celsius. So as I said, isotropic and anisotropic. Isotropic will H in all the directions. Anisotropic is basically it will give a specific direction. So in this, basically we obviously heard about HNA. We also read about TMH. These are both most preferred agent. So obviously they will be anisotropic agents. Uh, EDP, basically it is not that popular agent, but it is also uh, it is also an anisotropic agent. So but HNA basically in terms of etching, it will be isotropic in nature. So basically, although it is like it will give you can predict the etch rates, but the etching will be isotropic in nature. So etching will be in all directions. It does not give directional control, but it is still widely used because the you can predict the etch rate. So that is why it is being used widely used. Compared to all the three, HNA is the isotropic etching. So we'll move to the next question. Boron doping concentration at certain region can be increased so that this region will act as a mask and will not be etched away, and structures like diaphragm and cantilever could be obtained. There is no etching along 111 direction for a single crystal silicon wafer using KOH solution. These are basically you need. These are the question are recall kind of questions. So Sora has said this in the what do you say in the class videos. So these are the specific things which Sora actually said in the video. So from this question has been made. So the answer is only one is correct. So using boron doping, basically you can increase, you can make the region act as a mask, and you can prevent the etching from this etching happening, and you can get this kind of freestanding structures like diaphragm and cantilevers. Basic Coming to the agent, KOH basically works in one direction as well. So there will be etching basically. So that is how it works. This is kind of a recall kind of question, but like it's good to know. So we'll move to the previous year questions. So okay, so this is a very simple question. Doesn't require actually MEMS, but we'll still go through it. We like to fabricate a silicon cantilever. Cantilever dimensions are 200 micrometer long, 50 micrometer wide, and 20 micrometer thick. The sacrificial layer is made up of 250 micrometer thick SiO2. The etching solution being used has an etch rate of 25 micrometer per minute in the vertical direction and lateral etch rate of 2 micrometer per minute. So, what will be the minimum duration of etching required to release the cantilever? Do not worry about the anchor. So, this is the anchor. So, what they are saying is, in this figure, so basically you have you have this cantilever beam. So you have this sacrificial layer. So now what you are doing is you want to remove the sacrificial layer below the cantilever so that you can release it and you can have the structure moving. So as I said, in the anisotropic etching, the etching will change as per the uh, like etch rate will vary across the one axis. So here there is one lateral vertical etching rate and one lateral etching rate. And what they are saying is, since it's a hypothetical situation, they are saying don't worry about the anchor. It will always be, it will not get etched away. So now you need to find out how like what will be the edge duration to remove the etchant. So 8 minutes, 10 minutes, 12 minutes, 30 minutes, 25 minutes, or no, not enough information. I hope you understood the question. If you don't didn't understand the question, just let me know. I'll explain the question again.
So now here thickness is there, that will, let us assume that is the vertical direction side. Thickness is 20 micrometers, and the length is 200 micrometers.
So I'll just draw it out. So this is 200. Um, the width. So basically this direction. This is 50, and this height is 20. So now the thing is, according to this figure, you can see here, the cantilever is upstairs. So the sacrificial layer is at the bottom. So what actually in this case, what matters is only the width. In this case, basically the length and the thickness are of no use, because the you can see the sacrificial layer is downside the cantilever. So now what you have to do is you have to etch away this area, so whichever is downstairs. So like here you can see the down, whichever area is there below the cantilever, you need to etch it out. So what you are supposed to find out is basically for that width you will have the vertical etching and you'll have the lateral etching. So the etchant will come from here. So etchant will be coming from top. Barabar. So etchant will come from top, it will go down, but it will also be like, I'll just give you an example here. This is the uh, structure. This is the cantilever, obviously. So from here, the agent will be coming. So agent will be going etching it here, and it will also etch in the lateral direction, right? So now what you have to find out is how much time. So you have a lateral etch rate of 2 micrometer per minute, and you have the width of 50 micrometer. So how much, like, how much time will it require for the etching, for it to etch away? So that is what the question is asking. So would you like to solve, or should I come up, should I show the solution in the next in the um,
Sir, shall we add the tooth? Sir, now here, um, sacrificial layer is made of 250 micrometers thick.
silicon?
So
That is of
250.
no, that is to confuse you. That is basically to confuse you. That is not mandatory. So that
Sir, you are
is,
saying that we have to remove the sacrificial layer, na, sir?
yeah. So sacrificial layer is down below the
Yes, sir.
cantilever. So that does basically what we're saying is basically maximum it will go is for uh, because it has to 25 micrometer per minute. So it will go down till 250 micrometer is what it is just saying. It is like not a very important because it is the thick. Yeah, sorry, yeah, you need that information because you need to remove the 20 you need to remove all the 250 micrometer. So you need to know the that also. So sorry, you need that information. You need that information as well as the lateral etching information. So
250 by 2, okay, there is no
250
answer.
by
So,
25, so you'll have 10 minutes will be your answer basically.
vertical direction, will it be
Vertical
20?
vertical direction is this is 250, and in this
Okay, sir.
20.
Okay.
So basically you have two parameters here. This is the vertical edge rate. So now so I'll just explain this question in detail now. So you have this width, you have,
Sir, a separate white
oh yeah,
new.
yeah, sorry, I'll just do that. New slide. This, if the screen becomes invisible, just let me know. I'll just, okay.
Visible,
So
visible, sir.
now you have this cantilever, okay. uh, so what is since it is above this, the entire beam is above this, this is not of our concern. So what we are concerned with is this 50, okay. This is 250. So now what we have to do is we have to, like, I'll just change the color so that you will be able to understand better. So now what we have to do is using our using our etchant, we have to remove this area. So so as to release it. So the area which I'm marking in yellow, we have to remove it completely. So now there will be two H rates which will be coming into picture. So the first H rate will be the vertical H rate. So vertical H rate is 25 micrometer per minute. Okay. So if it was a isotropic agent, if it had only one direction, if it had equal H rates in all direction, what you need to do is you need to remove the 250 meter, this much area you need to remove. So in the vertical direction it will be 250 upon 25, which you get as 10. But now what is happening is, since the agent is coming from here, this you have to remove the down area, but you have to remove it this way, right? You have to remove this this way. So your lateral H rate comes into so your vertical H rate doesn't play an important role. Your lateral H rate comes into play. Okay, so your lateral H rate is you want to find out. So both side it is coming from this side also, this side also. So you have 25 from this side and 25 from this side. Okay, so to H that 25, so down basically it will go beyond. So now what you will have to do is you have to H 25 millimeters in the lateral direction, sorry, micrometers in the lateral direction, with an H rate of 2, because what is happening is it is eating up 25 in every minute. It is eating up 25 micrometer this side and 2 micrometer in this side. So it is every minute it is eating up 25 in this side and 2 in this side. Two, sorry, 2 in the lateral side. In the vertical side, the HND is eating up 25 micrometers of the silicon layer and 2 micrometers of the silicon layer below the cantilever, because below the cantilever the vertical etching is not happening. So you need only the lateral etching. So to release it from both sides, it is attacking. So to release it, you need to have like you need the HN to eat away 25 micrometer from each side. So you have 25 micrometer divided by 2, that is you have 12.5 minutes, because you need to release it from both the sides. So you need to it has to be more than that. But now what is happening is why the vertical H rate, why this question is important. If in case of 2, if they had given per se 8, okay, in case of in place of 2, if they had given 8, what would you get? 25 upon 8. So that is um, around 8, 3 point something something. Okay, so what will happen is, but you need the entire thing to be removed, like below the thing it has to be removed, below also, right? It will do is it will just remove the in this direction, it will also needs to remove in the below direction also. So in that case you need to know the vertical acceleration will also come into play. So in this case, so it will eat up vertically all the 250 micrometer of the silicon wafer layer. But since it is not able to release it, we are considering the lateral H rate. I hope you are able to understand this what we are saying.
So, it looks some typical, sir. Actually, we have seen first how to create. Not like this one, sir. We are not thorough with this cantilever preparation, sir.
No, this is basically not this. This is basically you just have to understand the difference between lateral etching and the vertical etching. So what from this figure, all you have to do. I'll just a moment. Sorry, sir. What I'll do is just a moment. I'll just reset everything. Just give me a moment.
Sir, no audio, sir.
Hello, is it audible now?
Yes, sir.
Yeah. So I'll just explain it again. It's we don't have too many questions, so whatever questions we have, we'll go in deep so that you can understand everything. So just we'll take a new slide only. We'll draw. Take a thinner pencil. So you take first silicon wafer. Okay. Now it has been oxidized on those things. Uh, like that is the standard MEMS procedure. So that you need not like uh, care now as of now. So what will be basically next step will be basically it will be they'll make a silicon wafer and they will be oxidize it and get this SiO2 layer. This is SiO2 layer.
Sir, we take the another color, sir, for SiO2.
Okay, I'll do that. I'm not that very good at drawing, and drawing on this computer I'm not very much used to. So okay, so yeah, we'll just show in this one only. Can you see the purple layer SiO2?
Yes, sir.
Sorry, this is just for as of now just please with my drawing. So now what will happen is sacrificial layer has been made as it is given in the question also. They have a sacrificial SiO2 layer. Now what is happening is in the third phase what is happening is they are taking a photoresist. So they'll just do the spin coating and they'll put a photoresist over here. So okay, so now you have silicon SiO2 layer, silicon SiO2 and photoresist. So in the third step, what will happen is now the you have the photoresist, you have everything. So now in third step, what they will do is um, they'll take a mask. So they'll take a mask here. They'll take a mask here, and then what they'll do is they'll put light. So that is called as photolithography. So after the light has been put, so all these areas will get solid will become solid, okay, and this will not become solid because we are using for positive photoresist. What will happen is these areas have become solid. So obviously it's not that simple. There will be a pre-exposure bake, there is a post-exposure bake and everything, but that is something which is not the part of this course, so I'm not going into deep. So there how it becomes solid and everything, there is something what is called as pre-exposure bake and post-exposure bake, but as of now it's not something related to your understanding, so I'm just skipping those parts. So now what will happen is this has become solid and this part what we exposed has become solubilized. So now in the next step what will happen is we'll take the wafer will look like this somewhat. uh, it has the SiO2 layer below it, and this has been solubilized resin, and this is the silicon. So now in using PVD, what will happen? PVD they will deposit using PVD they will deposit the silicon, the cantilever material. So cantilever can be made of any material. It will be gold cantilever, silver cantilever, copper cantilever. It doesn't matter. It will deposit using PVD. It will deposit. Then in the next step, what it will do Hello, sorry for the inconvenience. There's some campus-wide power suddenly went off. Um, so um, I we'll start again from where we were there before. Quoting.
Sir, audio not coming, sir.
Is it coming now?
Yes, sir.
Sorry, there has been some power issue in our campus, and suddenly everything is going off. Even I didn't realize for a long time. It's just a moment. Yeah. Um, so what will happen is, uh, as I repeat again. So you have a silicon wafer, you have a silicon SiO2 layer which is be marked in purple. You put the photoresist, you develop it using photolithography. Basically you expose it to light, you solubilize the exposed region. So now this region has been exposed, you wash it away. So you use some like basic ethanol or isopropanol and you just wash it away. So this is solid, so this region will stay. So the photoresist here will stay, but this didn't get solubilized, so it will just go away. So now what will happen is, deposit metal over that region. So now in that region you deposit gold or copper or something. Okay. So now once the deposition is done, what you will do is you will use stronger reagents. So there are some n-heptane or something like that. There are reagents. So I won't get into the names, but yeah, there are some reagents using which you will remove um, the so the solidified resin which was there earlier, you will remove it now. Okay. So now what you will get is the final figure that will have cantilever here. Below that there is a silicon oxide layer, and then you have a silicon wafer. So now what this question is asking you is, basically you have a cantilever of 50 dia. You have a silicon oxide layer here. So now it is asking you what how you means what how much time you will have to etch, so that you can etch away this much region which has been marked in light blue. uh, were you able to understand this question, the scope of this question? So it doesn't actually require you to understand the fabrication process. I'm just explaining it to you how the process works, but it doesn't actually require you to explain the know the fabrication process. All it requires you to do is to have an imagination of how you will release that much, how will you etch it out from below that cantilever. Anyway, you have been given the etching rates and etching parameters. So all you need to know is just like visualization, or just you need your visual capacity. So were you able to get grasp the process now? Basically, what I explained to you, were you able
Sir,
to?
now we have to consider my expectation is to cover width, sir, and here SiO2, whatever SiO2 thickness is there, we have to consider. I think the two
Yeah,
things.
yeah. So you have to you have to dissolve the SiO2. Now you have to etch out the
Just
SiO2
below the cantilever beam, we have to
cantilever.
do that.
Yeah. So you
So,
have the so now what is happening is, the challenge is, uh, SiO2, you it will come from here. Sorry, SiO2, you since the cantilever is there, you cannot just drop SiO2 from sorry, you cannot drop since the cantilever is there, you cannot drop your the etchant will be coming from here, but you cannot drop the etchant above the cantilever, because cantilever is uh, like you don't want to etch it, right? So you have to protect it. You use some cover, protective covering, so as to not destroy the cantilever. So now the etchant will come from this end and this end, so the vertical etching won't happen right below the cantilever in this area. um, in this area there will not be any vertical etching, so only thing that will happen is the lateral etching. So basically from this question you have already been given the lateral etching rate, so you need to find how much time you have to do the etching so that the area is etched away. So were you able to follow the question now?
So here, thickness, sir. Sorry. Width now. What is the width?
Yeah,
50 or
width is
25,
50,
sir?
50,
Then
50.
actually it should be 50 by 2.
No, no, no. So that is the thing. The agent will come from both the side, right? So agent will come from here. Sorry, uh, agent will come from this side. It will go at so from so just
That
agent will
process
come.
is not mentioned, sir. That you're saying that we should not take care of the
Yeah,
procedure.
that is basically your imagination, madam. So that you have to develop that imagination. So what happens, like whatever see even what I explained it to you, how the cantilever has been made, it's not mentioned anywhere. It is basically you have to imagine the process. When once you go deep into mems, in the world of mems, once you will go deep into the world of mems, no, you will be able to imagine the process. So obviously in this 4 week course you won't be able to do it. We have like I basically do it day in and day out. I have spent my time in mems, that's why I can imagine the process. It's not, even I am not foolproof or anything in that, but like this is how it will happen. You have to you maybe have to imagine. So now how it
Yes,
is
sir. It
happening is,
is true. It is true. Only with this problem we are trying to understand this process, sir. Otherwise,
yeah,
we are not considering this much depth, sir. It
yeah.
is
So
true,
it,
sir.
yeah, it will take time. You don't have to like, don't feel sad if you are not able to understand, just ask. Don't feel sad, it will take time. It will take months maybe to do it, so don't worry about it. So now you can imagine, right, why we are taking 25 and not 50, because
Yes, sir.
HNT is coming from both ends and you are eating it like this is from this end it is eating 2 micrometer per minute, and from this end also it is eating up 2 micrometer per minute. So your effective width is 25, because from one end whatever it will be from symmetrically it will be from the other end. So that is how it is working. So you need 12.5 uh, minutes, or that comes to 30 minutes, because obviously at 12 minutes it won't be done. So more than 12 minutes, 12.5 minutes, so that is 13 minutes. That is the minimum etching time you have to do it. So I hope you are able to understand it. If not,
Yes, sir.
just let me know. We can go through the problem again. We'll just go through other
Understood, sir.
problems.
Understood.
And so now the sputtering rate depends on the applied power, reflectivity of the material, melting point, and the surface target distance. So I explained you the sputtering process. So we'll just go again to that slide. Uh, yeah, so here you have this argon atmosphere. You have the sputtering target. You have the material, sorry, you have the wafer here, that is the substrate, and the sputtering target is basically the gold bar or some, or the copper bar it will be. So what will happen is the argon atoms will go and hit the gold bar, and it will eject gold atoms, and it will the gold atoms will go and hit the silicon substrate, and basically it will create a thin film. So this is how the process looks like. Uh, so based on that, what do you think will be the major factors that will the sputtering rate will depend on? So just a thing, there is no melting here happening of the metal here. So
Applied
the,
power, sir.
yeah, so basically it will be applied power and surface target distance. So if the as I said, the atom is going and hitting the gold bar, So the power with which the argon atom will hit the gold bar should be high enough so as to eject the gold atoms, and also the distance should be enough so that the gold atoms which are ejected will go and reach the substrate. It should not just because the gold atoms have limited power, right? Limited energy or limited. So it has to have like uh, wha- the ejected gold atoms uh, will also like they can't travel for infinity, though there is a specific distance it can travel. So closer the distance you will get a better result. So again, there is optimization and all those things required. So just this is how the process works. From the process you can imagine what are the two factors that can happen. So since there is no melting, argon is hitting, gold is coming out, so there is no melting of the substrate happening, so the melting point will have no role, and the reflectivity of the material will also have no role to play, because here there is no light or laser or anything involved. There's argon atom which is going and hitting the material. So that is why the only two factors which it depends on is the applied power and the substrate target distance. I hope it was clear. We'll move to the next question.
Sir,
So
can we say atoms, sir, or ions?
so basically, it is ions, but we use in this case in MEMS we are not going that much deep into chemistry per se. You can say atoms, and you can use them interchangeably because it is for at least for MEMS it's not like you don't like we like we don't be that specific in MEMS case, but yeah, it is basically ions, not atoms. But yeah, it is ions basically. Thanks for correcting me. So now here you have which of the following is 111 N type wafer, A, B, C, or D. Uh, I had shown you the figure here previously in the start. So from this N type, what is N type 111? You just look into it, and then we'll move to the answers. So N type 111 is N type 111 is the one with 45 degrees. So uh, the answer is C. So here you have the one this flat, and this is the 45 degree. So you have the answer here is C. So we move to the next question. How many atoms are there in the unit cell of silicon? 4, 3, 8, or 10? Uh, so any guesses? So the answer is 8. So it is a basically it's a FCC structure. So you can see here the silicon has an FCC based structure. So uh, this becomes 1 8 1 by 8 into 8, and this becomes 1 by 2 into 6. So basically it's not asking how many like this way. So it is just asking like number of atoms at like it is not basically asking the effective atoms. It is just the question is just asking you how many atoms. You just have to count. So you can count here 1 2 3 4 5 6 7 8, and like effectively it becomes the answer comes to 8 in one.
Sir, sir,
Yeah.
in the last class, he told some like diamond. I forgot the word after the diamond. It is not perfectly FCC. He told some other, which will start with the diamond, sir. That is the structure of
Silicon. Then I'll.
diamond. Diamond, after diamond, another word is there, sir.
Yeah.
Not FCC. That is also one objective question. There FCC is mentioned, and another, I forgot the title, and that is the diamond one. So FCC means 8, sir, but
8, yeah. So yeah, this even I got
yeah,
confused. Maybe I also. prepared it,
See,
but
in the middle one, on the how many sides will be there? Six. I don't know. Just
yeah, diamond cubic crystal structure. Yeah, it's
I
a bit
think I
different.
think.
Yeah, yeah, yeah. So since he has covered it previously, you just this. I'll not go into deep.
No, sir.
So
Only objective. In the objective, it came like that one.
yeah, yeah. So
Mm.
it is diamond cubic. So this is a question you need to like focus on. So basically, how it is. When when I yeah I forgot because I made the slides like month 1 month back. I forgot about this thing. Yeah, this question. Yeah, it is diamond like cubic structure, and the answer is 8. I'll just wait for some time. We'll just finish all the questions, and then I'll circle back to this question so that
Okay, sir. Okay,
we'll
sir.
get back to it. So commonly used p-type dopant are boron, lithium, indium, thallium. So p-type is basically the ones from the so there is n-type dopants and the p-type dopants. You have the carbon group. So basically carbon group is the silicon group from which the silicon belongs to. Then basically the p-type are basically before the before silicon, and n-type are basically after silicon. So basically n-type is basically boron group. Sorry, boron group are the p-type semiconductors, and the nitrogen group elements are basically are the n-type semiconductor, n-type dopants. So basically, for p-type dopants are basically the boron and indium, those kind of things. So basically, the ones which are from the arsenic and those things which are from the nitrogen group are basically n-type dopants. So this is a general uh, thing. Moving to the question number 6, HNA agent comprises of hydrochloric acid, nitric acid, um, acetic acid, sulfuric acid. So basically, it consists of hydrofluoric acid. So it should be basically hydrofluoric acid, not hydrochloric acid. So I'll just correct this here only. Hydrofluoric acid, HF it is not hydrochloric acid. So the answer is nitric acid, acetic acid, and hydrofluoric acid. uh, Coming to the seventh question, etching rate is maximum along which plane? 110 plane, 333 plane, 111 plane, and 100 plane. So basically this has been discussed in the lecture. The answer is 110 plane. So basically it depends on the atomic like the etching rate depends on the atom packing. So basically what happens is the when there are too many atoms, there will be boundaries. So it becomes very difficult for the etchant to go through it. Okay, so along the 110 plane, the atomic packing density is a bit lower. So that is why you are getting faster etching through 110 plane. So that is how it is. So 111 plane will have the slowest etching because it will have the highest atomic packing density along that plane. So there will be a lot of atoms. It will so your etchant will encounter a lot of obstacles in form of atoms. So that is how it is. So which when there are a lot of obstacles for etching, the etching will be slower. When there is when there are no obstacle, etching will be faster. So along the 110 plane, the number of obstacles will be less. So that is why the etching rate will be high. So moving to the next question, resolution that can be achieved by photolithography is limited by the wavelength of the light, intensity of the light, time of exposure, none of the above. So I should have explained it to you again, but I'll explain it now. So what happens is in you have this you have the wafer, um, you have this photoresist. Okay, Then you have this mask. Okay, and here from here there comes a light source. So now the minimum feature size that can be made from this, so light is coming down, so whichever in the mask which is blocking, where it is not blocking, it will come out. So now what will happen is, if the wavelength of the light, so light is in the waveform, right? So now if the wavelength of the light is too, like if it is too long, it will not be able to penetrate to the through the this hole only, right? If the wavelength is too big, it will not be able to penetrate through the hole only. So what happens is, because of these factors, the like the resolution is affected. So we need to choose a light source which has very short wavelength, so that it can penetrate through the this mask, and it can give us the good feature size. So that is why laser based photolithography has also come into place, because laser has the shortest wavelength. So since I had not explained this concept earlier, I will just give out the answer. The answer is the wavelength. So as I mentioned here, the light is coming. So light is, obviously light has a wave nature. It has a dual nature. It has photons and waves. So when we have the waves, it has to pass through the slit. So to the pass through the slit, the wavelength has to be less than the slit thickness. So that is what affects the resolution of the process. I hope I could explain it to you. Any questions?
Sir, photolithography means is it visible light, sir, or any other light, sir?
There are a lot of types. So basically, there is something. The light source is basically neon kind of light source, but there are laser also. E beam also has come. Electron beam photolithography is also there. Laser based photolithography is also there. The conventional photolithography has some neon lamp or something, helium neon, also, that kind of lamp it uses. So there are a lot of type of processes. So e-beam is also there. So in e-beam and laser based photolithography, basically electron beam will be the light source. So there are a lot of types of photolithography. E-beam lithography, since electron beam will be there, so it has the the best resolution it can get, because obviously it will have the like a good wave. The wavelength will be very short, right? Electron beam has the short wavelength. Then you'll have laser, which also again has short wavelength. So like the neon light or helium light, which are the vapor lamps which are used earlier, obviously they have a bigger wavelength, so the resolution in that case is bad. But again, cost and benefit, everything, e-beam is expensive, laser is expensive, these things are cheaper. So this is how the lithography is there. But there are various domain types of photolithography process. The conventional one uses like I'm not like the lamps would be there, so they were visible range. But now again there is e-beam and laser based photolithography also. There are a lot of processes. So this is basically the visible length. So the wavelength is the main factor. So should we move to the next question? So these
Yes,
are
sir.
the questions we had. So any questions you have, or we'll just circle back to this question, right? If you have any questions, we'll just take we just circle back to this question, and then we'll go to this go to your questions. Any other questions? So diamond like cubic structure, basically what it does is, basically these are 1 by 8 into 8. So this is one atom, and here these are single atoms is what I could check. But again I need to recheck it again. But I could not like do it again. So but so what I'll do is, I'll get back to it in the next session. So in the next session I will get back to you with the specific detail. So I also need to refresh things. So these are the very basic things I just ended up forgetting. I'm really sorry for that. But yeah, any other
Sir,
questions?
I am not asking the answer for assignment question, sir, but I think one problem is there, sir. I have to
Yeah.
check. I will tell you, sir. Yeah.
No, ma'am, I'll just check here only. No, I'll just can you just tell me the number of the? I will not share the screen. I'll give you a hint, but
Okay, sir.
if
I will check now, sir.
yeah, just tell me the number. I'll also check. Checking simultaneously on my PC also. I'll try to give you a hint. I will not. Like if it's sometimes these questions are even go beyond even my head, so I'll also try. I'll try to find a hint. A brief introduction to microsensors. Week 3 assignment, right, ma'am?
Sir, I read the question. Uh,
Yeah, ma'am. You can tell me the number, madam. I have the
seven, seven, seven.
7, right? Let's go there. Uh, what resolution in picometer could be achieved theoretically using e-beam applying an input of 25 kilowatt input. Okay, okay. So so the 25 kilowatt, I'm just searching the formula. So there is some formula for that. I'm just searching that which formula it is. It's there. Yeah, I got the formula. So this is the formula which you have to use. It was this formula, I think so, is not there in the lecture, or I don't know whether it's there. Are you able to access the chat, madam?
Yes, sir. You can share the
Formula.
formula.
So I'll just
Or if
share
it
the.
is there in the material, I will check, sir.
I don't know
I'm
whether
not
it's there
sure
in the
whether it
material,
is
because
there.
I had seen that formula. I just forgot
Okay,
what
sir.
the formula is exactly.
I will take
No,
the
no, I'll just
formula.
show you. I'll just write it there. I just give you that formula that much only. So here it is. Lambda is h is Planck's constant here. Uh, Root over 2 me. E is the electron. Is the um, acceleration voltage, and m is the electron mass. So from this your formula, you have to get the answer. Were you Are you able to access the formula, ma'am? Madam?
Yes, sir. But they're ask resolution. They're asking the resolution, sir.
No, resolution is the wavelength, madam. So what will be the resolution? So resolution,
Okay,
see,
okay.
um,
Mm.
and I'll just go to the where I explained it. So what is the resolution? So here you are having this wavelength, okay? So any feature size. So here we are saying when will the light be able to pass through the slit? Only when it is smaller than the wavelength, right? If the slit is bigger than the wavelength, so basically the wavelength should be less than the slit width. Okay, so the slit width is the minimum slit width that can be achieved in this process is the resolution. Understanding it, the slit width is the feature size, and the minimum that you can get and pass the light successfully is the resolution. and that resolution is basically dependent on the wavelength. So basically, the if the wavelength is very big and if it is not able to pass through that slit, see, I'm giving you in very simple language so that you can understand. So the technical
So
terms are,
then it is the minimum. Sorry, resolution. Okay, sir. Okay,
yeah, okay. So I'm just giving you in the simple language you can understand. So that is
yes,
how
sir. Yes,
what
sir.
the
Okay.
thing is. The formula, I don't know whether it's there in the lecture notes, but this formula I had they had like when we were taught, we had this formula. So I remember this formula. I was searching it. So just keep that formula for safely. Maybe they this time whoever is setting the paper, you can maybe you need to, because looking at the questions this time, whoever will be setting the paper also, it will these are good questions, so you need to
Sir,
like,
now this mass is the electron mass, sir.
yeah, mass of electron. So you need to search
Okay,
that, Google everything,
okay, okay, sir.
and to get it in picometers you need to like,
But in the last assignment also, where the answer is like a range, but we kept a single answer, and that is wrong, sir. Now
then
whether
you can raise the question, ma'am. You can raise the question using there is
here
sometimes
also
what
whether
happens.
we have to give the range or
No,
value,
no,
we do not know.
you have to, your
Okay,
value has to be within that range, ma'am.
how can we give the range, sir?
No, you don't need to give the range, ma'am. You have to give the
Okay.
value, whatever. If the range is like 8.5 to 8.8, your value, your answer could be 8.6 or 8.7 or 8.5 to 8 point, like whatever your answer is, it should be fall within that range. That is how it should be. If there is any problem like that, no, you have to just put that in the discussion forum. You just have to put raise that question in
So
the forum.
I will show you the assignment 2, sir, solution.
Okay, assignment two solution. I also
Yes, sir.
I,
Yes, sir.
I have the assignments open. Just give me
So
a minute.
that problem is in a big grill problem. And there they have given range. I think, sir.
What is oh, this question we solved in the class, no? Similar question.
Similar question, but we got single answer. But there they have given. You can check the solution, sir.
Yeah, yeah, type range. So your answer could have been between 0.30 to 0.65. So whatever, if your answer was 0.35, it would have been right. If it was 0.38, it would be right. So that way
Sir,
it does.
we need the solution, sir. Shall we arrange a question in the forum itself? Actually, this is over now, sir. We need the solution immediately, sir. We need the solution immediately. Now, sir told one of the like your colleague who took the
With
class
us.
in on Saturday. He
Yeah.
told that at the end we are giving. So not like that one, sir. Here we want the solution for the assignment. Uh,
I'll just check. Like what is the difference between this question and what we solved in our class? Like,
sir, the problem is I got a 67.591, sir. And that's why I'm asking here. I got very different value. Now here it is like this much small value. How it is a wonder 0.30 to 0.55.
oh,
That's why it need the
I'll solve this
solution.
question by my hand and I'll do it,
Okay, sir.
and
Okay.
I will get back to you.
Okay.
Maybe you can just what we did in the last class. You can just in the
I have followed the things, sir. But still, in the even seventh question also, my answer is wrong. That's why.
Okay,
What is
you
the
were right
mistake
with
I
the
got
units,
there?
right? Gigapascal, that
Same.
you what?
I will show you the my calculation also. But 6 and 7 are wrong for me.
Okay, I'll check whatever your answers are. You just type them out here.
Six.
I will.
Sixth
Yeah,
one is 67.591,
I just type
sir.
in the chat
Okay.
box.
Okay.
I will check and I will get back to you at next week maybe, and
Okay.
we'll do it. Else during the like the doubt solving session also we can do it. So next week, we since we have the agenda for next week, I'll do it in the doubt solving session. So there will be one more doubt solving session. So next week will be the second last session, and then there will be one more session. You will get intimation of that date and time later. So during that session, we will maybe solve that question, because that will be, we'll be deviating from the week 4 plan, right? So what we'll do is, I've made a note of it, and I will present the solution in that session, in the doubt solving session. Because now what the thing is, if I deviate from the plan for the next week, then it will be a problem for me. So I will share the solution in the last session. So that will be a doubt solving session. That will be a 2-hour session. Since many of you have given the doubts, I will start with those doubts only. Else what I used to do is, I used to revise the assignment 1 2 3 4. But I don't think this time it is essential. I'll just go
But
through
I
all your
have
doubts.
given the answer, sir.
Yeah, yeah, yeah.
Sixth
I got.
question answer and seventh question answer,
Yeah,
sir.
yeah. I'll just get the. Just take a
Similarly,
photo.
even in the assignment one also one missed question is there.
Yeah, just put those questions. I will just yeah, put your answers in the chat box, in final answer what you got, or the question number also you can put, and I will get that solution done in the doubt solving session. So maybe it will not happen the next week, because I cannot deviate from the plan which we have been instructed to do by NPTEL. But I will surely get it done. Don't worry.
Sir, it is the combination of the springs, sir, four springs. At that time, my understanding is like that one, and I took the. Can you guess this, sir? Sixth or seventh springs, four springs are there in the question, assignment one.
One, just a moment.
Eight question, sir. Eight question. At the time, my understanding was that, and I have took the third one is a right answer, but B is the right answer, sir. Eighth question, eighth question. K1, K2, K3, K4.
K1, K2,
Yes.
K3, K4, K4.
Assignment one,
Okay,
sir.
so this one we solved in the class, no? This one, madam.
Uh,
This one we have solved because
so all
both are
are
in series. So K1 plus K2, and all are in series. Because now what will happen is, they have given answer is
they,
B, right?
they
Barabar. So what is happening is, see, K1 and K2. Okay, they have. So what is series and parallel? So you have to understand what is the, for spring, what how you will do it. So in current, so you are from electronics background, or you are from which background, madam?
electronics, sir.
Yeah. So in electronics, what is the criteria to pass a resistance in series? So when the resistance is in series, the same current passes through it, right? The potential difference may be different, but the current is the same, right? When it is in the parallel, the potential difference is the same. The current will be different, right? Current will get split based on the resistance, right? That is the criteria to determine whether it is in series or it's in parallel, uh, right? For resistance. So for springs, the criteria is basically when the deflection is same. When the deflection is same, the you get them in parallel. And when the like the force applied, F1 is the same. When the force is same, it is in series. So here what is happening, the deflection of K1 and K2 will be the same, because so they are in parallel. And both, like, so you get K1 K2 and K3 K4, both are in parallel. That much you understood, madam?
Then, sir,
So last point I'm coming. So what will happen is the deflection of, so per se assume that the mass is moving towards, I'll just share the screen and annotate on that. So uh, present stop presenting, and I just I just so, just a moment. I'll just take that screenshot, and I'll put that on the, I'll just annotate that. I'll take a new slide. uh, is the image visible, madam, now? Is the
Sir.
image?
Ah,
Yeah. So now this will annotate and will show you. So K1, K2, this much you understood, right? Their deflection will be same for this pair. Deflection will be same, and for this pair, the deflection will be same. This much you understood. These both are in parallel. These both are in parallel.
that's why I kept that answer.
Yeah.
Uh,
So now I will show you why these two are also in parallel. So now what will happen is, just a moment. So this one is deflecting by delta x. Okay. So per se, if this is deflecting by delta x, what will happen is these if these are getting extended by delta x, these one are getting contracted by minus delta x, right? This one are extending by delta x, these one are getting contracted by minus delta x, so the deflection, so the net deflection is the same, although the direction is different, the deflection is the same. We are getting it, madam.
sir.
So the when the deflection is same, what is the what I told you, it is in parallel. So the springs are in parallel. So when the parallel it is, the formula is k1 k2 k3 plus k4. You getting my
Sir,
point, madam?
then now I have given one answer, na, sir. Then what will be the reverse, na, sir? If my answer is the thing, then what will be the construction, sir? Okay,
No,
they have given
that
construction. I you told the answer,
that
sir. But if
that is
my answer is there, then what will be the construction? That
yeah,
means
that is
two springs in parallel. Oh,
that will be no. That is the they these this construction will be there. The two springs are in your answer. Basically, two are in parallel. Two are so two pairs of parallel which are in series. So I'll just draw it to you for you. Just I'll just show you. It's a really it's a good question. So it will be like this. Okay. So this. So it will be sort of here will be this is movable, yeah. Whatever I'm showing will be movable.
sir,
This
now
is
screen is not.
I'll just
I'm not able to see the screen, sir.
yeah, just a moment. I'll just show it to you. So what is happening, you are having this fixed, this is fixed, huh? This is k1 k2. This is like a movable system, like this is like just just to hold it is, and then this is k3 and k4, and this is the block. So the deflection of k1 and k2 will be the same, because now what will happen is it will like it will be delta x, and this one will be the same, because but the like this one is this whatever this plate is there, this is a movable plate basically. So this plate will be moving, so this block of mass will be moving, then this will be pulling this spring, and then this springs will be pulling this movable plate, and then this movable plate will be pulling this spring. So you're getting my point. K1 k2 in parallel, because their deflection will be the same, because whatever will be the deflection of this movable plate will be the deflection of k1 and k2, and then whatever will be the deflection caused by the mass will be the deflection by of k3 and k4. Are you sort of able to understand this scenario, madam?
Sir, so here on the left side, all are having the same displacement, no, sir? In your
No, the K1 and K2 will have same displacement. K3 and K4 will have different displacement. So displacement I'll show you like this. It will be like so sort of this. I'm just showing the stable condition and the displaced condition. So just you have this stable condition. This is then what will be the displaced condition is, so basically just this much. This is k1 k2, and this so the displacement will be different. So you can see the length I'm showing, the forward pair is getting displaced more, and then once it is extended fully, the the second pair is getting pulled. So the displacement is different, it is not the same. So that is why this condition comes in series. So the deflection of k1 and k2 is the same, but it is not equal to k3 and k4. K3 and k4, the deflection is different. Like k1 k2 deflection is different from k3 k4 deflection. So that is the case for your the answer which you have given, madam. Are you able to understand, madam?
Okay, sir. Thank you, sir.
Yes, so I think uh, there is nobody else who has joined. So I hope I was able to make your 2 hours. I was able to uh, give you some information these 2 hours. So if you don't have any question, I'll just end the session. You have any
Okay,
questions?
sir.
Please let me know.
I have to cross check this concept, sir. But at the beginning, I answered assignment one, so that's why I am not made cross check, and that's why I missed this right answer, sir. But
No
when
worries,
the
madam.
grills program problem was explained, then I understood. Okay, four. You told that the four are in series,
Yeah.
but I mean I have not corrected this one, sir. In
No worries.
assignment one, I have not corrected the
No
concept.
worries.
I have not corrected, so that's why it is wrong, sir. Now
No,
you have
it
explained.
takes time because basically the thing is, bi- I am, I guess, very, because either most of them will be from mechanical background or most of them will be from electronics background. The thing is, I am lucky because my graduation is in mechanical, and my like PhD topic is based on MEMS like area, so I am able to grasp both the concepts. So it will be difficult. Somebody will be strong in that MEMS area, somebody will be strong in the mechanical area. It will take time. So
Okay, sir.
whatever it is, we will try to
Thank
solve
you,
it.
sir.
So yeah, if you have any questions, you can ask in the doubt solving session.
Okay, sir. Thank you.
Thank you for your time,
Thank
and see you next time. Thank you.
thank you, sir.
Madam, you can leave the call. I'll have to keep it waiting till 4 minutes, but I will also, you can leave the call. Thank you.
Sir, in which one, sir? Are you sharing mail, sir? Any mail?
My mail, I gave in the last class. No, I didn't give. Okay,
Then I
so
will.
you can see my email, my roll number, right? ME22D five
Yes, sir.
zero
Yes,
three.
sir. Yes,
Yeah,
sir.
that is just, you have to just add at the rate iittp.ac.in, iittp.ac.in. So like ME22D 503 at the rate iittp.ac.in.
IIT? Which one,
TP,
sir?
IIT
IIT?
TP,
PP. Oh.
T for Tirupati, P,
Tirupati, sir. Okay, sir. Okay, sir. Okay.
TP dot AC dot I. You can leave the
Okay,
call,
sir.
madam. I'll just keep it waiting
Oh,
for just for formality. Thank
okay.
you, madam.